So, and with that, I'm going to turn it over to Ben. So thank you, Ben, for presenting.
Yeah. All right. So my name is Ben Zimmer. I'm a software engineer at 3M, and I work in SEMS. It's one of 3M's corporate research labs. And you might not think of 3M as a company that does a lot of software work. I know I didn't really before I started working there, but 3M is a really huge company and has lots of exciting data and lots of exciting products that relate to computer science and data analysis. So it's a great environment for doing this kind of thing in. So this talk is a talk that I put together to give originally to a class of undergraduates at my school. I went back to give a talk there. They have like a seminar class where people come back, you know, once they've gotten jobs and talk about what they do, and their eyes kind of glaze over. So hopefully you guys will find this material a little bit more applicable to your work and your areas of interest than these undergraduates did. But I wanted to talk about big data, what it is, and then show a bunch of tools and technologies that these students probably hadn't encountered yet, but probably would at some point once they get out and start working in the industry. So just a quick slide here about like what is big data. I'm not the authority on this. It's kind of a buzzword, but this is sort of what it is to me. So big data is about new methods that are required to move, store, and analyze large amounts of data. So larger amounts of data than you can do in something like SQL Server or a relational database. Big data is about building these really powerful systems from commodity hardware rather than using specialized appliances. So you just can get a bunch of like workstations and put together a Hadoop cluster rather than having, you know, like an Oracle box or something like that. And it's addressing a lot of different needs. There's data warehousing, so like just storing data for a long period of time. Stream processing, mentioned that earlier, and data analytics. If you want to do your analytics at scale, you need special techniques to do that. And then the other thing that I think is sort of like a common trend that you see in big data technologies is frameworks and languages that use functional paradigms. So, and this just sort of comes from the way you have to deal with data. You know, if you're working with these huge data sets, you have to be able to describe how to work with it, you know, using parallel operations, and functional paradigms really lend themselves to that kind of work. And what it does is it brings supercomputing to the masses. I mean, 15, 20 years ago, I think if you wanted to, you know, use like a really big cluster, you would have had to like learn how to write MPI or something like that. And now with big data frameworks, you can write something in Java, you know, run a MapReduce job, or write some Java code or Python code to run in Spark, and it's like, it's really accessible. So that's one thing that I think is really exciting about all of this. So I'm an engineer. I like to think of things in terms of what's an engineering problem. So our task is to replicate a scaled down version of the Google Books Ngram viewer. And I don't know how many of you are familiar with what the Ngram viewer is, but it's basically this application that lets you put in Ngrams. And Ngrams are just like a single word or sequence of words that are found in text. And then it shows you how often they occur over a period of centuries. They have this huge data set. So like, just as an example here is the two words Apache and Cassandra. I can maybe add Spark to it. And I'm searching here in American English and smoothing out the graphs a little bit. So you get this graph. And this is just a really massive amount of data that's being searched and called up here. So the question that I would ask, and the undergraduates had no response for this, is how would you go about implementing this? What languages and tools and platforms would you use? Does anybody want to suggest anything? Yeah. Yeah, Solar actually probably would be a really good way to do this. I haven't used Solar too much, but so here's what we're going to do. We're going to build this using virtual machines in the Microsoft Azure cloud. You could do this in Amazon. Doesn't really matter too much. Apache Cassandra, Apache Spark, and we're going to use R and Shiny for the visualization web interface part of it. So Apache Cassandra is a high-speed, high-performance distributed database. This really unique ring architecture where it has no single point of failure. This is one of the things that I think is really neat about Cassandra. Something like Hadoop HDFS, there's a single point of failure in the name node, whereas Cassandra, every node in your ring sort of behaves identically, and each ring doesn't store all of the data, it stores a subset of the data, but each one behaves identically, and any one of them or multiple nodes could fail, and you still have all of your data. It also offers tunable consistency, which means that like on a per query basis, you can choose if you want to, if you want speed or like accuracy in your results in terms of how your results compare to like new updates that are coming into the database. And the data model of Cassandra is particularly suited to this problem. Like Cassandra sort of presents itself in a way that sort of looks like a relational database where you have a table with named columns and things like that. But under the hood, it really stores data in more of like a map, where you have a map of rows that have different numbers of columns. And that's particularly suited to this problem because what we're trying to do is we're trying to call up words and have a time series basically for each word that is the usage of that word over time. So I'm going to just kind of skip through a little bit of the cluster setup stuff here. Apache Spark is a framework for parallel computing, and it's more flexible than Hadoop. Hadoop is probably pretty common and pretty well known at this point. Lets you solve problems using the MapReduce paradigm. But Spark is more flexible, lets you do MapReduce, lets you just do all sorts of other things. It's really nice just for running like batch parallel tasks on a cluster. And it offers Scala, Java, and Python APIs built right into it. I'm a big fan of Scala. I'm just learning it, but it's really impressed me so far. And the other thing that Spark gives you is it gives you a interactive shell, which is really nice for like just interacting with data that you have stored in a parallel sort of data store. And there's a connector library for Cassandra for Spark. And hopefully we all know what R is at this point. One thing that I want to point out is that R's vector and string processing capabilities make it really nice for working with a cluster. I use R on the command line when I'm setting up clusters and doing things like that all the time because like you can, maybe run a command and get a bunch of output from different machines and then like use R to parse it, load it into data frames, sort it around. It's just really nice for that sort of thing. Okay, so I'm just going to kind of skip through this, but basically our steps are to allocate these VMs using the sort of Azure web interface. Log into each machine and disable SE Linux because that's just going to cause you a lot of grief later if you don't. Set up passwordless SSH. So this is a set of steps you'd go through manually for a small number of nodes. For a larger number of nodes, you're probably going to want to find some different way to do this. But basically what it lets you do is you can log into one node, and then you can log into the other nodes securely without having to type your password each time. And this becomes important because you want to give the nodes nice names, and then you want to have a utility that's going to let you run a command on all the nodes. That's going to accelerate the setup process. And it's really impossible to do that without setting up passwordless SSH. I just wrote a shell script to do this, but there's all sorts of utilities that you can find for doing this. And by the way, I think I might have skipped over this, but we're using virtual machines that are running CentOS. It's a common free Linux distribution that's often used for high performance environments, clusters, things like that. Install R in RStudio Server is one of the things I always like to do first on a cluster. Install Java. And then both Cassandra and Spark are very similar in the way that you install them. You basically just download like a pre-built binary from the website, and then you just extract it, and then I always put it in /opt, and then I add a symlink so that it has a nice name. So like the file might be downloaded and have like this long name where it has like the version number on it, and I just give it a symlink so I can just go /opt/Cassandra and get at it. And then I put it on all the nodes, and then you have to configure a single file mainly so that the nodes know where to talk to each other. And then you just start it up by running the Cassandra service on each of the nodes. And when you have it running, you can do this. So I'm telling this tool called Node Tool to connect to Cassandra running on a machine called cass0.ed. And it's going to give me a little status, and hopefully we'll see that all the machines are up. Yeah. Let's see.
Are you connecting through Wi-Fi? Where are your machines?
They're in the Azure cloud.
So you're connecting through Wi-Fi?
Yeah. Yep. So I'm just going to rerun this with the wider. So each of these machines is holding 20% of my data. They're each holding about 20 gigabytes of data. And that token is like sort of a marker that determines the partition of your data that each machine holds.
Is there redundancy or not?
Say what?
Is there redundancy? Like you do this redundancy?
Yeah. Yep. And you can choose what that is. So the way I have this set is I have 5 Cassandra nodes, and I have it so that all of my data, each piece of my data exists on 3 nodes. So. Okay. And Spark is very similar to set up. You basically just extract this application, extract this file, put it in a common directory on each of the nodes, do a little bit of configuration, and then start it up. And once Spark is running, you can visit a URL and you'll see like a application page that shows your Spark workers and your applications that are running. So in this case, there's a Spark worker that I have running on each of the machines that sort of allocates and sets aside a certain amount of memory and cores that applications can use to run on the cluster. And these machines are each like 8 cores, 14 gigs of RAM. They're pretty small. You wouldn't really want to run Cassandra on such small machines in a production environment, but it works. And then a final step is installing the Spark Cassandra connector. This is basically just downloading all the right libraries. That's the tricky part. And then putting them in a folder on each machine. Okay, so I'm just going to show some R code here. So when you go to the Google Ngram Viewer page, there's a link to this page that describes where you can download the data yourself. And it lists all these files with all these links you can download. So what I did is I used an R application. I just downloaded a copy of that HTML page. Then I used an R application to read in the HTML as XML and then like search through it recursively to find the hyperlinks. And then I filtered through those to find the all the lists of the files I needed to download for the English US 1 grams, 2 grams, and 3 grams. So separate lists of like just the single word frequencies through the years, and then the pairs of words and sets of 3 words. And then I save those out to some text files.
Hey Ben, just out of curiosity, how big were the text files?
They're not too big. There's basically just like there's like a couple files for each letter of the alphabet and each number. But then the individual files that you download are really big. I wasn't sure how big the data set was, and I ended up only downloading the 1 grams. But the same approach would work to get all of the data. You just have to have a bigger cluster, more storage on each node.
What does that mean? Is that in all the print? This is how frequently?
Yep. There's
all copyright for print data or something?
yeah. So basically, the data looks like there's like a word. So like a column for each word or n-gram, and then a year, So like each word and then for each year. And then for each word and year combination, there's like a total match count and then like a volume count. So the match count is like how many total times it appeared in all books in the Google collection in that year. And then the volume count is like how many individual books, how many unique books the word appeared in. So then I was going to get fancy and use Spark to distribute the downloading and insertion of each file into Cassandra. So what I was going to do is I was going to basically have each machine in the cluster be downloading different files and parsing them and inserting them. But that ended up being a little bit too much to have Spark downloading these files and inserting them into Cassandra running on the same nodes. So I just ended up running it on one machine. But I still use Spark to do it. I'll just show this quickly, kind of what it looks like. So Spark has this interactive shell and that you can run Scala in. So what I did is I just wrote these little Scala scripts that I would run in the shell. And of course, it's not showing the syntax highlighting quite right. But I think what I've learned about Scala is that it's kind of like a nice bridge language in between something like Java and something like R or Python. If you're used to sort of like the functional paradigms that you have in R and Python, like list comprehensions or applying functions, you'll see a lot of this in Scala, like maps and things like that. And it gives you a really nice syntax, really clean syntax for lambdas. Like here, I'm mapping a function x where x is this. X is a parameter to that function. So makes very nice, small, clean code that does a lot. So I think, if I remember right, it took on the order of like a day to download and load all of the data. And I just ran a count because I want, and this is just for the 1 grams. I just ran a count on it earlier today using Spark. You can see the Spark application running here. Like counting how many things you have is not like a strong point of Cassandra. It took about an hour for me to count the number of rows that I had. And I think, let's see here. So this is what the data looks like. You've got the n-gram, the year, and then the total match count and the volume count. So this is an interactive Spark shell, and the result is like 1.2 billion rows when it's stored like that. The thing to point out, though, is that under the hood, Cassandra is actually storing this as really long rows. So there's 1 row for each n-gram, and then the columns of the row are like the year and then each of the counts. So you'll have like a row for each individual word, and then the row is the time series. And the rows can have variable numbers of columns. So in order to build a little application to use this data, I had to overcome a hurdle, and that's when Cassandra originally was sort of put out there, it had this interface that sort of exposed the Cassandra store for what it actually was, which is that sort of long row, uneven number of rows kind of thing. And I guess people thought that was unintuitive, so they made this wrapper for it called CQL3 that kind of gives you a more nicer table structure like this. So when I'm showing this data, this is looking at the data through CQL3. But there's an R Cassandra package, and the neat thing about it is that it uses just the pure Cassandra like binary interface. It doesn't use Java or anything like that. But it was written before CQL3. So I wrote a wrapper around it that takes the really messy result that it gets back when you query that table as just a like from the Cassandra CLI, the old style Cassandra perspective, and then rearranges it into a nice data frame that matches what you see from CQL3. So when you query the data, what you end up getting back is like, so I'm basically doing a query by ngram. So like I'm saying, I want all of the, like the whole time series for the ngram Apache. And what I get back when I query the data with our Cassandra looks like this. It's like a big data frame of all these raw values. And what it is actually is it's like, there'll be like 1 year, so it'll be like, say like 1989, and then it'll say 1989 match count, and then the value for that column, and then 1989 volume count, and then it'll go through that with all of the years sort of as rows. So this function sort of unpivots that data into a nice table that's easier to work with. And then from there, it's just a simple matter to write a nice little shiny application. So here's our little shiny UI. And then the server basically just grabs a connection to Cassandra and then pulls from some input, does a query. Some of this code is just basically, if you're asking for multiple ngrams, it does them all separately and puts them back into a list. And then does a nice plot where it figures out the maximum margins, maximum graph size that's required, and plots each of the lines separately. And it's just all done with base R plotting. So when we run it, it looks like this. And it's pretty fast too, so I can Yep. So it's some of the other sort of NoSQL kind of tools that you might see don't quite have the response time that Cassandra has. Let's take sort of a fun example. And then let's extend this out to 2008 and add Google. 2008 is the last year. Oh, Google just surpasses IBM there in 2008. And then I added a smoothing function that should be more or less identical to the smoothing function that the Google Ngram viewer has. That was a real pain to figure out, the smoothing function that they were using.
So there's no Spark in the viewing class.
No.
You fiddle with it for the loading.
Yeah. And then there's one more application that I use Spark for. So when this graph isn't just the raw data from the database, it's scaled by a total count of ngrams for each year. So like earlier, say like when you go back to the 1500s, there just aren't that many books compared to, 50 years ago. So they scale the data points by the total number of ngrams for each year. And I originally downloaded, they provide total counts files, and I originally downloaded one of them, and I just had a heck of a time getting my graphs to match up with what I was seeing in the ngram viewer. And I later discovered it was because I was using the British English total counts and I had the American English words. But to work around that, what I actually did is I wrote a little Spark application to find the total counts given my huge data set. And I can show you what that looks like. I'm going to just copy it into a file in RStudio here, so it's easier to see. I'm going to get rid of this comment. So this is just code that I ran in the Spark interactive shell, and this is all it took. to do this. I think it's pretty cool. So basically just importing the Cassandra connector. This is creating an RDD, or a resilient distributed data set, out of the Cassandra table, where I map each row of the table and I get basically the year and the total count. And then I do a reduce, and then I collect my results, and then I write it out to a CSV. So I don't know how many of you have written Hadoop MapReduce code, but compare that to the amount of Java boilerplate and Hadoop cruft that you'd have to write to do that with Hadoop. I think that's pretty cool. And you can see here the beautiful Scala syntax for lambdas and things like that. So this took, I think it took about an hour to run. I had to crank down my Spark core count so I wasn't competing with cores between Spark and Cassandra to get this. But then once I got that, then it looks right. And it's really, really close to the actual correct counts file from Google.
How long did it take you from end to end then?
To what?
To create this, to create the output of the Shiny app?
To make the Shiny app?
From beginning to end, like how long did the project take?
Oh, I don't know, maybe 12 hours. I don't know. I mean, that's cluster setup and everything too. The Shiny app maybe took me like, I don't know, 3 or 4. And most of that was like fiddling with the graph to get it to look right, the plot.
Why aren't you in Mountain View, California?
Yeah, I work with them, so don't take it.
Yeah.
So was it Spark or Cassandra that decided your multiple 3 partitions or 3 duplications of data on 3 nodes?
It's Cassandra.
That's Cassandra's
Yep.
decisions?
Yep.
How many nodes could you put it on?
Oh, I've heard that they've run Cassandra rings with thousands of nodes. I don't know.
And is it usually 3 copies of all the data? Or?
Yeah, I don't know. I think it would depend. I think you'd probably, on a really big cluster like that, you'd get, depending on what your use case was, you'd get better performance if you increase the replication. What happens when you query Cassandra is it goes in there and it sort of figures out what nodes the particular piece of data that you're after is living on, and then it kind of hits all of them, and then depending on what you want for your consistency, it sort of it'll give you back just the first one it hears from, or it might wait until it gets a couple of them back and then gives you the one with the newest timestamp. So,
Piggybacking off that.
yeah.
If you run Spark against Cassandra,
Yeah.
does it make sure that the locality, that the locality of the data, are they linked up? Is the connector that strong, or
Yeah.
is it possible that you're doing processing on one node?
Probably each, I mean, within a single Cassandra query, you might be hitting who knows which node. And that's just kind of how it gives you good performance, is it spreads the work around. Like you can make the same Cassandra query to any node, and as long as your data is consistent, you're going to get the same result. And that query might involve that node talking to 3 or 4 more nodes.
So, but Spark, when run on HDFS, is actually going to have that data locality.
Yeah. Well, it would have been more performant for me to just have a separate Spark cluster. And just,
Since it's not, yeah.
yeah, since there's no data.
Yeah, and I think it's probably, I don't know, it's probably more correct to consider. I mean, Spark could be considered to be part of the Hadoop. I mean, MapReduce, the Hadoop ecosystem includes MapReduce,
Yeah.
but they're not the same thing.
Right.
So you can use Spark in the Hadoop.
Yeah.
So I wouldn't make the distinction of saying Hadoop and MapReduce are not simply saying that they're the one thing.
Right.
I have to say that
Well,
there's a Hadoop ecosystem. You have many different programming paradigms.
Yeah.
One of them is MapReduce. One of them is Spark.
Yeah. Well, the thing that I would point out about Spark, and I won't talk too long about this, but Spark is sort of designed to work with Hadoop out of the box, so you have that compatibility with an HDFS. But the cool thing about Spark is that you're not chained to that by any means. So there's no HDFS in this system. I'm just going against Cassandra. And in fact, you don't even need any kind of distributed parallel data layer with Spark. You can just run it on machines and just store data on your local disk. It'll, as long as you can distribute the data that you need to work on, it does that in memory. You don't need to have any kind of parallel file system.
When it divides the data up, does each machine have to have the same size of chunk?
It doesn't necessarily, and they use sort of hashing mechanisms that are designed to spread stuff around. But basically how it works is like for each word, it sort of, or n-gram that I have, it hashes that, and that determines which 3 of the nodes that data is going to live on. So then when I ask for one of those time series back, it does that same hash on the key that I'm asking for, and then it can find it really fast. And then the downside to that is, like with Cassandra, there's no distinction between updating and overwriting. So when I write, every row has to have a unique identifier, and if I write to a row that has that same identifier, it's just going to overwrite it. All right, I think that's it.
So thanks for coming, everyone. And Jeff, did you have something to say?
Hey, if March 7th, if you think you're gonna be there and you're 100% committed to this whole idea, and you aren't gonna give a talk, we might still love to have you as a volunteer.
Good point.
And I'll check people in or do some editing. I'll share that form too.
Yeah. All right. Thanks.